To understand a planet hot enough to melt lead, you have to build instruments that can take the measurement before they liquefy. At the surface, Venus bakes at 900 degrees Fahrenheit, under an atmospheric pressure 90 times greater than Earth's sea level. Between orbit and the ground lies a dense, violent barrier of sulfuric acid clouds. To pierce that barrier, NASA engineered a split-mission architecture known as Pioneer Venus. It maintained a safe observation distance while penetrating the atmosphere. The entry payload was the Multiprobe. A central cylindrical bus carried 4 distinct cone-shaped descent vehicles, 1 large probe and 3 identical small probes. Scientists orchestrated a coordinated siege, deliberately crashing 5 separate vehicles at once to gather direct evidence from the depths. In 1978, 2 Atlas Centaur rockets carried the mission components off the launch pad and out toward the inner solar system. The orbiter component was built for endurance. Its primary job was to map the planet remotely using radar from a stable, high-altitude position. Engineers staggered the launches by 3 months. This ensured the orbiter arrived first and established its position before the probes made their approach. The orbiter entered the observation, freeing the multiprobe to strike directly into the hazard zone. By November 1978, the multiprobe reached the vicinity of Venus and began to physically divide millions of miles out. This technical schematic of the probe adapter structure shows how the hardware was arranged for deployment. The large probe sat perfectly aligned along the central spin axis of the carrier bus and was released forward. Days later, the bus accelerated its spin to 48 revolutions per minute, using centrifugal force to hurl the 3 remaining small probes tangentially off the main structure. Looking at this plotted grid, we can see exactly where the north, day, night, and large probes were targeted. They formed a massive, simultaneous strike pattern across the day side, the night side, and the high northern latitudes. Hitting these extreme geographical points at the exact same time gave scientists their only way to capture a complete, global cross-section of the Venusian weather machine. The probes were falling into the same atmosphere, but they used entirely different methods to survive the descent. The large probe relied on a heavy protective heat shield to bleed off its initial velocity, followed by a parachute deployment at an altitude of 67 kilometers. The 3 small probes carried no parachutes. They plummeted on purely ballistic trajectories, relying strictly on aerodynamic drag to slow them down. Inside their titanium pressure vessels, the probes carried tightly packed instruments. Mass spectrometers mapped the chemical composition of the air, while nephelometers fired lasers to measure the size and density of cloud particles. Engineers specifically tailored the descent speeds so these instruments would have exactly enough time to sample distinct layers of the atmosphere before hitting the ground. This diagram illustrates the entry trajectories for all 5 pieces of hardware hitting the atmosphere simultaneously on December 9, 1978. The carrier bus entered at a shallow angle. Lacking a heat shield, it survived to 110 kilometers, measuring the upper ionosphere before burning up. The 4 remaining probes drove deeper. They absorbed massive deceleration forces, swallowing temperature and pressure readings at a frantic pace. Data had to be instantly beamed back to the parabolic antennas of the Deep Space Network before the crushing atmospheric pressure ruptured the transmitters. For 55 minutes, the probes executed the most highly choreographed, data-rich descent in the history of Venus exploration. The descent ended with a brutal impact. The probe struck the solid 900-degree surface at 22 miles per hour. They possessed no landing gear and were never designed to function after impact. Yet, against all engineering odds, 2 of the small probes survived the crash. The day probe went a step further. It sat on the scorching alien surface and continued to broadcast a signal for an incredible 67 minutes before heat and power depletion finally killed it. That accidental survival provided NASA with the first extended, direct measurements of the Venusian surface environment by a U.S. spacecraft. The data extracted from those destroyed probes, combined with the orbiter's long-term observations, finally stripped away the planet's secrecy. The instruments confirmed the extreme density of the atmosphere, mapped the distinct layers of sulfuric acid clouds, and tracked high-speed circulation winds. Over time, the orbiter's radar penetrated that permanent cloud cover entirely, returning detailed topographical maps of Venus's craters, mountains, and fault lines. Operating long past its expected lifespan, The orbiter maintained its lonely vigil and transmitted data back to Earth until 1992. The mission's dual architecture allowed NASA to map the surface from above while simultaneously sampling the environment below, replacing speculation with 14 years of hard data.